So, hello everyone, again welcome to my channel, and this is my second video regarding the quantum mechanics. Those who are interested in physics, they may refer this channel or refer this video. This video is mainly about what is the explanation of Schrodinger, what is the history of Schrodinger against the quantum mechanics. If you are in 9th or 10th class, you may read this quantum mechanics chapter in which you find very little concept. Very little concept means black body radiation there is not present, but Schrodinger is present. Only there are two equations, small equations. So these are not very applicable. When you are proceed towards the higher classes, you will find many applications of quantum mechanics. If you are reading BSc physics honors or MSc, then you may find these things very much deep history about the Schrodinger. So let's start this video. So see, there is one thing written in first here is written the transition from deterministic description in classical mechanics to probabilistic distribution in quantum mechanics. Okay. In this classical mechanics, it is proven that Heisenberg uncertainty principle, the position and momentum simultaneously of a system with the same accuracy by using the R known. In this Heisenberg, you will find that the momentum position and momentum is not find or unknown, but here is written known. So the classical mechanics is deterministic in nature. To prove the classical physics, it is said known, or in Heisenberg, you will find that this is unknown. Okay, that is the main difference here. So here you see in the quantum mechanics, when a microparticle is in motion, this is history. Here you will not find basically the interest. Okay, now I am coming the interesting part. First interesting part is the wave function. Okay, so see, the wave function is basically the space-time behavior of moving particle can be described by function. This is the function psi rt. It is a measurement of probability of finding a particle about a position. Okay, this is a basically the denoted means this is the symbol you may say to determine the wave function. You may say the psi r t. This is the position vector and this is the time. Okay, basically this. And what is the characteristics of wave function in the Schrodinger's theory? Okay, Schrodinger really will so help in physics to solve to explain these things like wave function, probability density, probability. Okay, so what is the characteristics of wave function? We may read this. So wave function is single valued, continuous, and finite. It is a square integrable function. See, its magnitude. We already read this. This is the mainly this is the wave function, and it is the large in the regions where the probability of finding the particle is high, and in the small in the regions where the probability is low. Okay, it is the probability density. It is the basically the it is the definition of probability density. It measures the probability of the particle around a particular motion. Okay, now see the probability density. The probability density of a particle is the probability of finding the particle per unit volume of a given space at a particular time. Probability density is basically denoted as the square, okay, the mod square, or you may say the magnitude square of the wave function. This is the basically the probability density. Okay, there is the one interesting fact, that is the minus infinite to plus infinity, and this is mainly, you may see, this is mainly the one equation, you may say this is the normalization vector of the wave function. Okay, this is basically when you find that the question is given there to find the normalization, so you may use these things to find the normalization. And this is one interesting fact explained by the schrodinger. And here you see one is given a minus iv. This is the complex form, complex part, imaginary part and complex part. This is solved here. A and b are the real quantities and I is the imaginary quantity. This is explained, smallly explained. And here is the one written, the one dimensional wave function is L to the power minus half. One dimensional wave function. There you find many kinds of wave functions, one dimensional, two dimensional, three dimensional. The deep history is given towards the quantum mechanics. So this is the small parts which are explained by the Schrodinger towards the quantum mechanics to solve the various problems for normalization. See, I have already explained this normalization wave function. Now you find the superposition principle. The superposition principle states that if any Schrodinger differential equation has several solutions, psi 1, psi 2, psi 3, these are already explained. Psi 1 is there are the various wave functions, linear combinations, A1, psi 1. Okay. Here you find the probability of finding the particle, the A1, psi 1. See, A1 is basically the probability of finding the particle in the state. Where you mainly do the problem, there you will be given you a state in the normalization form. This is mainly the A1. Okay, so A1 psi 1 is mainly the AN is the coefficient of the corresponding state psi. There is already written there. Okay, so now you find the wave functions. One numerical is given there to find the probability. See the probability, how is it is finding. Here is given the one question. The wave function is which is in the quantum states psi one, phi one. Oh, sorry, phi one. This is phi one, phi two, phi three, phi four, and phi five. So one by root three times. So these are the coefficients. Okay, five. So the problem is given to find the probability in the psi five region. So you need to find the p five. So take the coefficient and square it, psi 1 square. I already told that in the previous two problems. Problems no means the area explain this mod a1 square. So take the coefficient here and square it and find the total probability. Also find need to find the what is the total probability. Okay, this is the problem. Here is one again problem is written. There you find the normalized wave function. How to find the normalized wave function? See, I already tell that the normalized wave function is denoted by this equal to 1. Okay. So orthogonal wave function is mainly the C naught. This is mainly the problem. See, these are the very tough problems you need to find. I am already telling in the video that interesting facts I will discuss. So if you are interested in these numericals, you may call me or you may message me for these numericals. I will explain. Now I'm moving to one interesting facts. These are the numericals, various numericals givens. All are of the same facts. Okay. Same normalization form is given and you need to find the normalized wave function. All are given. See, now is given one interesting thing there is. These are given the operators in the quantum mechanics. What is operators in quantum mechanics? This is one new thing you may find. A operator is a mathematical rule that changes a given function into a new function. You, if you are in new higher classes or see in the colleges, you will find that vector calculus. In vector calculus, there you will see the various vectors like this given. In the vector calculus, really you find this very things easy to learn. If A is an operator, it is generally represented by A cap. Okay, this is explained by schrodinger. X square it gives. See, partial derivative here is done. So commutator of the two operators is given. Commutative form, non-commutative form. If the cap is zero, then it is commutative, and if the cap is non-zero, it is non-commutative. There is find one thing. You need to find the derivative, and there you find the zero, so it is commutative. Normal problems these are. Here is given one thing: momentum operator. The wave function for a free particle in the positive x direction is psi x not equal to a e to the power I into kx minus omega t. This is mainly the wave functions, okay? And this is the real function. You need to know the derivative to find the derivation to find the this equation. Very much important and very much tough also to memorize this. But do not care if you are an if you are really physics lover student, then you may find it very easy to learn. One is given energy operator. This is I h cut del by dt, del by del t. Okay. And what is given the physical significance? It is impossible to measure the position and momentum simultaneously along the same direction with the same frequency. This is the Heisenberg's position momentum uncertainty principle. These are already said earlier. Now you see eigenfunction and eigenvalue. These you already know in mathematics also. Eigenvalue and eigenfunction. If you do the matrices part, then you find these two things, eigenfunction and eigenvalue. These eigenfunction and eigenvalue are not same as the mathematics, so do not correlate this. This is mainly the see here is written the operators. In the quantum mechanics operators, it is given these functions. The a cap fx is equal to c fx. This is mainly the function. Okay, eigenfunction is given by this equation. The if an operator acting on a function will always produce the same function by a constant factor. It produces the same function. See fx. Here is also fx, but here is one constant given. This is the mainly the eigenfunction. This equation is called the eigenvalue equation. It is the eigenvalue equation. Okay. Why sine square x is not an eigenfunction of the operator? D square by dx square. See, if you do the derivative here, and you may see 2 minus 4 sine square x It is the answer. By derivative, double derivative of sine square x is this. So see, most of you will become confused in these facts that why, and most of you will suggest this that this is the eigen function, but this is not the eigen function, because see, here is written the c of fx is the mainly the eigen function. I already said in the earlier. So c of fx here is the 2 minus 4 sine square x. Here is 2 minus means here is given one more numerator, means one more number is here. So how can you say this is the eigen function? See, one more problem I will say, then you clearly understand these things. See, cos x, I will say there is minus 1 is the coefficient. But here is the 2 minus given, so this is not the eigenfunction. So here I am ending this video. You may suggest this as very interesting to learn, and I suggest you that I will recover your all queries regarding this video, and you may say about the normalization of wave functions. There is various numericals are there given. When you find any problem, then please message me regarding the quantum mechanics or you may say this Schrodinger's, any problem you may say. There is, this is the half part only, okay? I am recovering this half part. Whole part is not possible in the one video, okay? I will try my best to complete the second part in the next video if possible. So please refer this, and you may any find these problems very difficult, you may say me, or interesting things you may say also. So thank you for watching this video. Please like, share, and subscribe. Thank you.